everyone. Welcome to this week's grant seminar. Our first speaker is Akshuna from Imperial College London. Aksh graduated from New York University in May 2018 with bachelor's in both math and physics. And after that, he went to MIT as a research assistant. And in fall 2019, Aksh joined the School of Engineering and Applied Science at Harvard University and worked as a research fellow. And since fall 2021, he has been a PhD student with President's Scholarship at the Department of Mathematics, Imperial College London. Actual research interests are dynamic systems, information theory, together with machine learning, quantum information, fluid mechanics, and number theory. So without further ado, let's welcome our first speaker. Aksh, you may start.
Hello, hi. Thanks for inviting me very much. Just a sort of mild qualifier. My main interests are only dynamical systems and information theory. Through them, I've sort of been able to do some work in other fields, but those are not my expertise or main interest. Okay, so I'm here to present something that I call mathe-physical perspectives on deep learning. It's part of a sort of research, for the lack of a better word, a research program sort of thing that I started while I was at Harvard. And it's sort of, looking at deep learning through well-established, well-existing theories, in mathematics and physics. So without further ado, let me sort of just, get to that. As part of those mathe-physical perspectives, I'm going to sort of show two applications, to things associated with deep learning. One of them is going to be about error analysis for neural network equation solvers, which I assume would be very much in the wheelhouse of this group since you guys invented pins. And the second one is an application of Koopman operator theory to understanding optimization. And so that one is more sort of driven from a dynamical systems flavor. Okay, let me get right onto it. So, just as a setup, I assume that you've sort of got this closed bounded path connected domain in some R to the power D. And there's a subset of that domain over which there are certain constraint conditions, which is to say that whatever you are trying to model, what the true model is at this subset of the domain. And it can be anything. It can be boundary conditions, it can be data from some sampling process, etc., etc. And so the setup for this entire thing is, okay, let's say given unique constraints over that delta D, delta fancy D, over which your constraint conditions, that you've got a solution to some differential equation phi. And sort of we start at the point in saying that whatever that differential equation is, you can always sort of break it down into saying, so that differential equation is sort of represented by this non-linear operator, for the lack of better word, f. And the point is that you can always write f of phi is equal to 0, as in, the solution maps, to the 0 in the appropriate functional space. And so you sort of start at the point that you can always break down your differential equation into terms that are linearly dependent on your solution, terms that are non-linearly dependent on your solution, and then terms that are completely independent of your solution. And so that's sort of like the basic setup, as in okay, this is how, you would set up the problem. And, just for the sake of discussions, for now, we will just assume that any kind of function we are, sort of interested in over D is analytic, just to make things simpler while we are discussing this. And so, neural networks are a very viable approach to modeling differential equation solutions. And, pins are very, very famous example, DGM by, I'm sorry, I forgot the name, but there's a professor at Oxford who came up with this other thing that, usually what you do is you basically just set up this network, that also maps from D to the appropriate R space. And for the sake of this talk, we are just going to assume that the neural network is composed of analytic activation functions. And so, there are sort of theoretical guarantees just due to the universal approximation theorem that say, okay, well, if you've got a feed forward neural network with even as simple as something as ReLU activations, we can approximate any Lebesgue integrable function over D. And then, there are other guarantees. Okay, that network has to have at least width this much and depth this much. And, so all those things are sort of existing work that have been fleshed out for a few years now. So they're part of this, existing literature. And, usually what you would do is, how you train these things is you train your model to satisfy what the truth over this portion of the domain, the constrained domain. And then you obviously try to minimize the differential equation itself over the portion of the domain you do not know anything, right? And so that's how, in a sort of overarching way, that's how the optimization of these neural network differential equation solvers go. And, there are other guarantees on the use of stochastic gradient descent, and, it's many variants that, you're always capable of getting arbitrarily close to the global minimas. And so, in the setup of this problem, we sort of assume that for now, again, for the sake of discussion here only, that phi was a unique solution to, whatever constraints you were given. And so the idea of this optimization is, okay, well, as L goes to 0, we are sort of expecting N going to the true solution. So that's how most neural network differential equation solvers, including pins, would work. Okay, so here are sort of like the basic, there are very basic observations that, that underpin the entirety of this work. And those are, okay, let's define this difference function, basically, that is, the error in your model, right? Phi minus N. And here are some observations about it. Let's just look at the loss function again, 1.1. So the first thing you sort of notice is that the loss function is, at least on the surface of the problem, not explicit in the error. It's explicit in the error over the boundary conditions or the constraint conditions, but there it's sort of like, you already know the true model, so it doesn't really help you that much, right? And so it's sort of, yes, you assume that when your f of n is going down, somehow your error is going down, but that connection to the loss function is not explicitly made. And so you have this ambiguous relationship between the loss and your error over d minus partial d, as in the portion of your domain where you do not know the solution. And as such, the error is usually only estimable over the portions of the domain where you do know phi, which sort of sometimes, defeats the point of making the model in the first place, because you can only sort of unquestionably trust it over the portions of the domain where you already know the solution, right? And since achieving L is equal to 0 is highly unlikely, because, just because you can get arbitrarily close doesn't mean you're always there. You'll get to the point, right? So what ends up happening is when you're optimizing, most of your optimization just ends up being in that, the region of optimization where you get very minor gains for each coming iteration, and this is a classic sort of observation in deep learning in general. You have that steep drop off in error, and then sort of this gradual march to whatever asymptotic performance the network can reach, right? Except most of the time is spent getting close to that asymptotic performance and not in that steep drop off, right? And so we were sort of trying to figure out how to tackle these three major, what we consider not exactly weaknesses, but sort of things to improve on in neural network differential equation solvers. And sort of we hit upon this sort of very simple idea, which was okay, since you start off with saying, okay, we are going to give our equation operator the model, and we are going to minimize f of n, we sort of try to give it first an explicit relation to the error. So assume that you have optimized your network to a certain point, right? And so now you've stopped refining your model from this point onwards, right? So what you can write then is that f of n is just the dependence on the linear term, the dependence on the nonlinear term, and then whatever independent term, right? And you do this very simple algebraic manipulations, and you end up actually having a sort of explicit dependence, because remember, the loss function is composed of this f of n here, right? And so very simply, almost, you do end up having an explicit relationship between your error and your loss function, right? And as you can see on the right hand side of things, the only thing that is unknown to you is the error. So you have this new equation essentially, right? Because like, you know, your equation operator, you know, once you stop optimizing your model, you know your model as well, your model function, right? And so the only thing that is unknown to you is this error, right? But it is explicitly codified in combination with the loss function now. And so you end up having, you know, just like you start with a differential equation, you end up having another differential equation. And, you know, you can sort of, for simplicity, sometimes I write this term as sort of this n dash term, but that's sort of just, you know, aesthetic. And so, you know, this term is obtained using some transformation, right? Like you have to do something. I mean, you can always reach up till this step, but if you're trying to get to this, you know, sometimes you can achieve this extra term. You know, what I mean to say is that you can sometimes, so you can see that the model and the error are both in the arguments of this n term here, right? Sometimes you are actually capable of sort of making them multiplicably separable. So, you know, so that the analysis is a little bit easier. And, you know, as always, Taylor expansions are one way to get, to get to it. There are other ways as well. It's not exactly needed. I'm just saying there's this thing you can do that makes formal analysis more amenable. You know, and so you can also sort of rewrite your equation in these terms. And, you know, this form is also useful because, you know, assuming that, you know, these higher order terms are not that important, you know, you get this like new differential equation that's actually very easy to, you know, analyze. Especially since, you know, and it also gives you these like very sort of verifies these common observations, for example, that the loss function and so, you know, so the norm of the error and the norm of the loss function usually sort of goes down together, you know, those sort of things, right? This equation, these forms sort of make this type of analysis easier. And in our work, we have a more formal proof of all of this, but for now, you know, just for the sake of discussion, you know, just as I said. And then more importantly, what ends up happening is that you can actually set up a set of new neural network or multiple neural networks if you're trying to do higher order corrections that can be used, because remember, the situation now is exactly the same as the situation when you started. You have a new differential equation, you have a set of functions that you know exactly, right? You know the exact form of those functions, and you have this unknown function that you would like to target, which is this phi epsilon, the error function, right? So you're actually back to square one in some sense, right? And so what you can do is you can set up another neural network differential equation solver, which basically just this time aims to resolve phi epsilon rather than the true solution free. So, you know, you can sort of call it true error instead of the true solution, right? And we also sort of know exactly when we should do this. We should do this once the original, like, you know, the original network being optimized is sort of reaching its saturation stage, you know, where optimization doesn't really need to that many rewards in your training. So what you would have is, so you can sort of encapsulate the, you know, algorithm if you wanted to, is, you know, you start off with this sort of, what you would call sort of, you know, your original model. You train it as far as your model trains according to whatever optimization algorithm you used, right? You construct the error PDE, as in the PDE to which the error is the solution. You know, you take your freezed model and you sort of, you know, now train over this new PDE with a new neural network. And now you have this error corrected version of your model, right? And so, you know, just to give you an example, we pick like a nonlinear Poisson-Boltzmann equation just because it has some, you know, nice applications in multiple fields.
Excuse me, can I ask a question here?
Please, please.
Hi, this is Panos Stinis from Pacific Northwest National Lab. So
Hello.
If you go back to your algorithm, what you have written here is a neural version of what is known in ODEs as deferred correction method.
Yes, it is.
Yes. So here, your first order, let's say, approximation would be given by n, and then the second neural network will be what there is called the error, right? So you find an equation for the error, which has as the right-hand side the error that comes from the first order approximation that you have. The difference is that you use Taylor expansion to get an equation for the error, while in deferred correction, they use their Lagrange interpolation, or in spectral deferred correction methods, they use a spectral approximation. Yeah. Yes. So all I'm saying is that you can also try to put what you are doing in this more general context of deferred correction methods. So have you thought about that?
Yeah. So let me sort of like, thanks for that point, because it's actually very relevant, right? You'll notice that up till this point, right? I haven't actually used Taylor expansions or any expansions at all, right?
Exactly.
I'm starting off with just explicitly relating your error, your loss function with your exact error, not some sort of order correction, this, that, nothing, right? And so from this point onwards, you're very correct. We could sort of, you can take these multiple branching paths, right, that are essentially just, figuring out a way to add a order correction, like a first order, or if you want to go all the way like to n orders, then keep on generating more and more differential equations at each step of the process, right? Then sort of a couple of major differences are, but you are very right. Like in sort of principle, you could just say that we are basically taking what do you call it? We're basically combining like classical numerical analysis techniques to neural network differential equation solvers, So in some sense, this N doesn't even, not in some sense, this N even doesn't have to be a neural network, right?
Exactly, yes.
Yeah.
So what you have there as the difference of the two, of the nonlinear term evaluated at two arguments,
yes,
in the deferred correction method, at least in ODEs, would be the integral if you write the equation as an integral form, which is the difficult part to approximate. And here you write it as n prime, and then n prime you expand in Taylor expansions.
Well, that's sort of the major difference that I was getting to. In this example that I've given you, right, I'm using Taylor expansions to make a point, but in general, you can actually, and we'll sort of touch upon how to do this, you can actually just work right off this term itself. So, and that obviously lends it to sort of like more, what do you call it? Like it lends more generality to the method, essentially, right?
Yep. Okay. Thank you. I'll ask more later. Thank you.
Sure. And so I'm sort of going to come to this example as well, because it will also touch upon the point you're making, right? And so let's say you have this equation operator F, right? And so what you have is, okay, you have sort of this, your equation is going to look like the Laplacian of something plus the sinh of something plus some independent term. And just to sort of like force a situation where we can compare things easily, I'm going to give a G this particular form for a particular reason that I'll just show right now. And then obviously my neural network is not going to be told anything about the true solution in any way, right? And so this in this particular form, the solution of the equation is something like this. Simple to, sort of like set up, easy to compare with. That's why we went with this example. And so similarly, we wanted to sort of see how well the neural network and then the error corrected neural network could do over a minus pi comma pi hypercube, like an n hypercube domain. And, you sort of enforce at the boundary, the solution is 0. So you just enforce it directly, right? And so this is sort of what like the solution looks like the true solution, simple to, interpret, right? And so on top, you have this, the original model. For example, you could call it the original, like if you were sort of using the pin, then in some sense, this is the original pin model. And I'm sort of, I'm giving the MAV values on top just to sort of give a sense of how accurate or not accurate the nth order corrected neural network is. So for example, the true solution should have 404. This has like 433. So decent performance, but there's some, there's a lot to be left in terms of like how well it has been optimized. And you can see below that even just a one order correction is an insane improvement over the original model. Not only that, the error estimate itself is quite well made, that the resources that were used. So what we essentially did is, what we are saying is, don't use the resources, the computational resources you're using to sort of make minor improvements on n after a certain amount of time, use them to make major improvements on whatever the error is at that certain amount of time in optimization. And you can see that there are very strong improvements in that regard. It's like a slightly more complicated where tau is taken as 5 instead of just 1, just for comparison purposes again, right? And so this is what the solution should be. And you can see again, that the original model and in comparison with the error corrected model, and the improvements are very significant. And we also made this sort of figure on saying, okay, well, what happens if you inject this error correction at different moments in time? So essentially what we did is we set up a standard network, let it run through all the way to the end of its optimization, right? Made a few copies at certain, like 50% of training, 75% of training, 90, 95, 99, right? And sort of injected order, these error correcting neural networks were of the same size, same activation functions. Everything about them was exactly the same as it was for the original network. The only difference was the PD they were operating on, which was this error corrected PD instead of the original one. And again, you can show that the class, for example, the continuity class of the error solution should be the same as of the true solution. All these things, you can show decently formally. Not decently, you can show them formally, and we have in our work.
Can I ask a question? Where do you attribute this? Is nice. Where do you attribute this favorable effect? Is it just because you didn't normalize properly? Because you now have you're in the small number regime, and the error equation has basically the same magnitude numbers, and so if normalization was working properly, you would have gotten this in the first place. Or is it just you're actually assisting the optimizer to do this? What is the explanation here?
So the major reason, there are sort of two advantages to to this error correction regime. One of them is sort of analytic, as in you can do analysis of your equation to give proper bounds on what kind of loss function values should correspond to what kind of error bounds, all that stuff. The second one is practical, which you are seeing in this figure, which is to say, look at the original optimization, for your original model, right? Like most cases, you see there is this asymptotic drop off in performance, right? There's a saturation of performance. Per iteration, you are gaining less and less improvements in your, in your model, right? So my main attribution of this, orders of magnitude of improvement is that, the new model, which is initialized completely, randomly again and separately and doesn't know anything about the previous model, right, is not in some sort of local minima that may or may not be arbitrarily close to the global minima, right? So essentially what you are giving it is more, freedom of movement in finding the solution, right? Because once the original network is in, near some local minima of optimization, it's hard for it to find a new one. Once what I mean to say is once it has reached some sort of saturation in its performance, right? Whereas
right. I get the point. I get the point, but this is exactly what we see if we switch at that point. Let's say this what we call yellow line. If we switch to LBFGS, we get exactly something like that, a big jump down, or small, making the learning rate smaller. But basically, LBFGS from Adam to LBFGS, we'll see this type of improvement.
Are you saying you would see this improvement if you switch the optimization algorithm at this point?
Yeah, exactly. In all our papers, we do Adam and then LBFGS, and we see a jump. So maybe Lulu or anyone who does this all the time can pitch in and say what their experience are.
Sure. So my sort of point here is that I'm sure that improvement is also considerable, right? But what I mean to say is this error correction can always be done, So even if you saw the improvement in LBFGS, I assume that improvement also would start saturating at some point in the optimization, right? At which point, if you bring in another error correction, you would be able to improve on that. So what I mean to say here is this sort of technique, it's a relative technique. It's supposed to be injected once whatever you're using has reached its saturation in performance.
I would like to see actually another level of correction, because I've seen errors 10 to the minus 5. What I have not seen is errors below 10 to the minus 5. So it would be nice to see if you inject another correction, let's say on the yellow, so you're reaching the yellow line, you go down, and then around there, around, let's say at 250,000, let's say. Sure. You iterations, you switch now to you introduce another
order.
Yeah. Then what will happen? Yeah.
So that's again something, and actually something both fortunate and unfortunate, because I just added, we are writing a manuscript here, right, obviously, and I just actually added a set of figures to that manuscript where you do see the correction all the way to E-8. How about I don't have the figures in this talk, but let me sort of show you those figures at the end of it, just if there's time.
Yeah, that's great. Thanks.
All right. So, but sort of encapsulating this portion of the talk, I would like to sort of end here is, as I said at the beginning, there is not a great amount of sort of fancy new mathematical techniques introduced here, in this particular work, even though the very simple set of transformations does allow you to do, it does allow you to prove powerful bounds on the performance, formally sort of state why you should expect the norm of the error and the norm of the that operator term to go down in value together when optimization is happening, to show that one major criticism that you would make just straight out of the bat is saying, okay, well, remember those observations you made at the beginning of this talk. You haven't really, by adding this error correction and a new PDE, you haven't exactly answered them. You have just sort of knocked them down to the next order, right? Because you could sort of raise this same set of points, hey, well, all those things you said about the first PDE are now true about the second PDE and the second model. And again, that, it's easy to, not easy, but it's possible to show actually you do get this, you can basically prove this convergence of higher and higher order things to the true solution. So, as I said, the two, nothing complicated is being done, but there are two very major, practical benefits you're getting out of this exercise. One, in terms of the performance you're able to hit, and second, in terms of the sort of formal analysis of your problem you can do, which is somewhat, which is a little bit lacking in the community in comparison to, and so that was sort of the main motivation for this work. And very nicely, the work
Hello, this is Lulu from Japan. I have another question here. So it seems to me from this figure, the earlier we do this correction, the better performance we have, also the faster. Can we do, let's say, after 1,000 iteration, we do the correction in the very beginning?
Well, so at the very, so we are, this is an excellent point again, right? For example, let's say you hit a correction here, right? There you won't see the benefits of your error correction because your original network itself is in this regime where it's, where it itself has this degree of freedom to find the fastest, the fastest path to better performance, right? So there, your relative improvement in performance is not going to be significant, if any at all. You really do have to, wait until you reach a saturation in whatever original algorithm you're using. As I said, this is this technique is supposed to be a relative injection. You hit it once you've reached a stage where you can't go any better with whatever you were using, at that point in time. And in that sense, I'm sorry, I forgot the name of the person who was raising this point, but in that sense, the technique is basically just taking ideas from, error, numerical analysis, and putting them on neural network equation solvers, right? So that's why I was saying there isn't as much as new stuff being done as much as there is as old ideas being used for powerful applications. Does that sort of answer your question?
Yes, thank you. And I have another question. In some cases, not in all cases, but in some cases, we may see the area saturates, let's say pretty early, let's say maybe 10,000 iterations. Then
Sure.
maybe you do another 10,000, it drops. So do we consider this further stage of saturation should eject or not?
That's an excellent point. You're basically asking, how do you know this was the right point, right?
Yes.
Like, how do you know? And so that brings me to what, sort of inspired my second work on these directions, that is both related and not related to this first project. And so before I get to that work, I want to sort of like get to like a more larger question, which is like, what the hell is deep learning in some sense, right? I actually, as soon as I raise that question, I'm going to sidestep it for this talk and the purposes of what we are concerned with. We'll just say that for now, we believe any, so the optimization of any multi-hidden layered network is deep learning, and just leave it there. I'm not going to try to like go any further than that, right? And to take it a step further, I'm also going to constrain myself to deep learning pursued via iterative optimization methods only. So no one-shot learning, none of the other fancy things that are being developed in the field that are very promising. But for now, I'll just keep to the classical stuff, right? And so within that set of constraints I've made for my problem, you can always imagine optimization as this like sort of discrete instantiation or this manifestation of a smooth trajectory in a high dimensional weight bias space. So essentially that's what is happening, right? You have this optimizer, it forces your set of weights and biases to go on this complicated trajectory in their, in whatever space they're sort of initialized in, right? And so just to formalize it, let's say you have n weights and biases, and they are within the real numbers, and that they are constrained to move within some subset of r to the power n, right? And your optimization scheme algorithm is called capital T. The number of iterations you have taken is small t, right? So you can literally write down optimization as this algorithm, like WT plus 1 is equal to TWT, and that's really it. This T might have many forms, but the idea is sort of like the classical dynamical systems view, or the continuous dynamical systems. You would say, okay, well, this thing is actually some sort of discrete manifestation of this thing, where you have this dw by dt equal to some, flow in the state space. And pictures always help. So basically you initialize something, thanks Wikipedia, by the way. I'm sorry if I did not credit them actually. And you're sort of forcing them to some minimum of optimization, and that's what it really is, right? And that's a very useful, powerful setup, like perspective from setup, but in reality it doesn't really offer you that much, because you can have trillions of weights in your network, and dynamical systems theory since times immemorial has always been problematic when it goes any higher than a few dimensions. So easy to set up, hard to do anything useful with, except when strong assumptions are made. And so there is this form of dynamical systems theory called Koopman operator theory. And what is it? We will sort of define it in a vague sense a little bit anyway, which is, so imagine the set of the space of square integrable functions on your domain, on your state space, right? We'll call that fancy F. And so if I had to like literally say that in a sentence, I would say that Koopman operator theory is essentially the theory that pushes you from a state space perspective to this observable or functional space perspective. And the Koopman operator is the object that forces that transformation. Many of you might recognize the Koopman operator as just the sort of the physics name for composition operator. And so the centerpiece of the theory is the Koopman operator. We will denote it as fancy U. And as I said, essentially you sort of lift your perspective from the state space to the space of quote unquote reasonable functions on the state space. Again, for the purposes of this talk, we are not going to get into details, except in this case, I guess. Sorry about that. So for all G in F, the Koopman operator is given as this object. So if you have like this discrete dynamical operator, then it's this object that forces this action. If you have the continuous one, then it's this object, right? And so, that's what Koopman operator theory does. And so the Koopman operator theory is the study of this object U. So what just happened when we did that? We took something like our perspective that lies in a possibly nonlinear finite dimensional case to a definitely linear but also infinite dimensional case. So you're trading sort of like one problem for the other. Why do you want to do that? And there's an interesting sort of reason for that, partly based on the modern advances in numerical methods. Since in most sort of systems of scientific interest, the class of functions that you're interested in is quite small, right? Like even if you consider statistical mechanics, for example, right? You can have who knows how many state variables, but when it comes down to it, the set of functions or the set of things you care about is actually quite small in comparison, right? What you can, because of that, what you can often do is you can work with compressions of you or projections of you, depending on which side of the mathematical lingo you prefer, over the relevant functional subspace. So basically, you take that large Koopman operator perspective and focus it only on the relevant subspace of functions, right? And so what you do is you compress or project your Koopman operator onto that subspace. And this is where modern advances in numerical methods have come in, because there was a time when, obviously this is still a decently complicated numerical computation. You can't actually do it by hand for anything more non-trivial than a few hundred dimensions, or even a few observables, but computers to the rescue, right? And so this is also why you might have even heard of Koopman operator theory in the last 2 decades. It's had a resurgence. It was invented in 1930s by Bernard Koopman, had a sort of 5-6 decades of dormancy, and then rose again in the last 2 decades in some sense, and has been applied to like a set of many interesting applications.
Akshuna, we had the talk here 2 weeks ago on the Koopman operator, so you don't need to say all that.
Okay. I'm sorry. I'm very, very sorry. Anyway, so let's just brace through this a little bit then. So let's say you have a set, you have a set of observables that you care about. So obviously you would have this, the same principle applied to them as well. Now, how is it relevant to your neural networks, right? They're usually trained using highly non-convex, nonlinear cost functions, which is an excellent observable from the Koopman perspective, because it's simple to track and it packs a lot of information about your network. Then, of course, the identity map itself is another excellent observable, that because it gives you information about the movement of your weights itself. A compression over a part of that, or a subpart, the whole space, if possible, would allow you to optimize the network without actually having to use the loss function. And so here's since everyone actually had an introduction to Koopman operator theory, we'll breeze through. It's just applying the same theory to that particular subspace. And then lastly, the spectrum of the Koopman operator gives you information about the state of your dynamical system. So this is where I'm again very sorry. I think the person asking me that last question was Lou, but I'm very, very sorry if I've forgotten that. They were asking, how do you know what's the right point in optimization to inject it? And the answer is actually, simply by observing, your network as it evolves, you can actually pinpoint, okay, well, the spectrum in a rough overarching sort of the spectrum of the operator has this property at this moment. This tells us, hey, we should, we have reached some sort of local minimum or saturation point. And so, as I said, KOT had a resurgence due to like a lot of modern computational tools. Dynamic mode decomposition is one of them. Here's a formula on how to use DMD, but it's sort of besides the point a little bit. The use is the important thing, right? And so we got interested in figuring out the use of Koopman operator theory to like actually both predict the optimization of the network and also characterize it. So to speak, like, okay, well, tell us where we think the variables are going to end up on, which variables are going to be what you would call sort of relevant and non-relevant, and also when you should expect your optimization to be done, right? And obviously, since we are the ones optimizing the network, we know what the weight bias dynamics are. You are easily able to read them. So you set up the DMD method that I introduced before, right? We got a few standard NN optimization examples, so like MNIST, the differential equation solver, which was the beginning of this in some sense of like, my interest in Koopman operator theory, etc. We got CFAR as well, classic examples. Figures are nice again. So, the idea was essentially, okay, you optimize somewhere here, you train your network to about some point here, like a few iterations or something. And then you use Koopman operators to push it to the final, both to predict the final state and then to push the network to them. Was it a success? Yes. The one shot, ironically, at the end of the day, it became a one-shot training method. Even though at the beginning of this talk, I said we would only consider iterative optimization methods. We were able to predict these states, like thousands of iterations ahead of time with very, very basic tools. Like I'm talking the easiest off-the-shelf tools you could find. And we did not make any assumptions about like activation function, weights, depths, optimizers, stars. We had a whole random mix of those going on in our experiments, and the versatility of the theory shown through in everything we tried. Obviously, one of the reasons to do it would be that you're getting some sort of like, so it wasn't just the characterization of your optimization, it was also, well, can you make it more efficient? And we were also able to obtain a significant speed up in that. And so the work appeared in NeurIPS 2020. It's called Optimizing Neural Networks via Koopman operator theory. The first work, the characterizing work, and then relevance and irrelevance and all that stuff are on archive, not yet still in review. And and then the promise figure, 3 orders of magnitude improvement. So, Koopman operator theory had something significant to say about optimization of these things. We had to sort of skip. I promised that we would say something about.
Let me ask you something. When you introduced this, 2 years ago, right?
Roughly 1.5. Yes.
Why not everybody is using it?
Well,
because you're making big claims here, and if you're right, I will drop what I'm doing, drinking a smoothie right now, listening to you, and do this. Why not everybody's doing it?
I would say so. I would give.
The reason I'm asking is you didn't show us any result. You showed this final result, and we don't know really how it works. You sort of high level. We know what Koopman theory is. You show this result, and then nothing in between. So your claims are kind of a little iffy, to put it mildly.
Yeah, no, that's fine. That's a very
and nobody. And I don't know. I know lots of people who are doing this, and nobody is using it. Although I like the Koopman operator theory, but why is people are not using it?
I would say a little bit. I wouldn't say like exactly that completely nobody is using it. We do have some level of what you would call pickup on it. We have a few people that have used the technique and a few citations of it. One of the other reasons I would say is you're right. In some sense, the initial idea, it's still in development, is what I would, like the first NeurIPS paper, right, was sort of this proof of concept work, right? And so the second, what you would call like more strong application of it came out like just literally a few weeks ago, and the third one is still in works. So essentially, you're right. Like it is just me and well, not me, but like my other collaborator, who was also responsible for like introducing this set of methods, who are currently driving this.
Okay. Can you say something, because you said every example that you try? Can you tell us which examples have you tried? Because that's an important work. So I'm trying to give you credit, but we need some evidence.
So maybe I sort of made this presentation a little bit wrong. Can I show you?
You can show us anything. Panos is doing Panos Stinis, who asked you earlier, the Koopman operator, but I don't think he's using it in this context.
Sure. Give me just a second. Let me show you, like, let me give you a table that I really should have put here, actually. You are very right.
Sorry, we are a little skeptical in this group.
It's okay. Skepticism is both warranted and useful. You don't have to justify it. We are doing science here, right? Give me just a second. So our initial set of, give me just a second. This is going to be a little bit rough to show, but that's on me because I did not put it as I should have. So the initial set of optimizers we tried were like Adam, Ada Grad, and Ada Delta. And this was on the neural network differential equation solvers. So we were using, NND solvers to solve dynamical systems, essentially, not essentially, like exactly, right? And so here's sort of like the different sets of architectures we tried in this particular example, the optimizers. And then T by T was sort of this idea of, well, there was this comparison, there is this idea of like how much faster you get, which was, a good couple of orders, 3 orders of magnitude, depending on like which system you had, right? And then there was this idea of like, well, how accurately are you able to do it? And so the most, like sometimes we were fully accurate, as in like, all 100 examples we set up were charted exactly well. And sometimes, I think 85% isn't bad, especially when you have 2 orders of magnitude. But yes, at the same time, there were what you would call not perfect, tracking or perfect modeling of the dynamics. We also tried Koopman training an MNIST network. So, this sort of like the visual representation of that network. We have this, the green dot sort of shows this, dynamics of like a couple of the, weights and biases of that network. And then the dash dots show you like how well or badly the network was tracked. So you can see like this dynamics is a little bit easier to track. So you pretty much have like exact tracking. This one gets it, but not quite, like, that there's sort of trade-off in saying like, okay, well, is it really finding the fixed point, or the, is it not? That's, and again, as I said, this work was more proof of concept than anything else. And that, I would assume, is the main reason, it only got a moderate amount of attention and has gotten a moderate amount of attention, rather than you dropping everything and doing it just about now. We have tried this with a different optimizer, a much larger architecture. So this is like a good 20,000, 30,000 weights and biases, I would say. And so I know this might not be as satisfactory an answer, but unfortunately, I
excuse me. So did you use this for neural network, neural ODEs?
We used, do you mean neural ODEs as in from that work neural ODEs, or do you mean neural networks being used to solve ODEs?
Neural networks used to solve ODEs, because that's what I understand. And my question was, yes, you have these results there, but we don't know for what kind of systems did you use it. Was it a 3-dimensional system? Was it a 3 million dimensional system? You see, because finding the Koopman operator it's not, it will have its own expense, right?
Yes.
So and you may get a speed up of being able to go 1,000 iterations, but the question is also how expensive it is to actually find this Koopman operator.
The construction cost is incorporated in this speed up comparison. So we have the construction as part of this calculation.
Right, what is the system underneath that you?
Because it's not scaling up. If I have 1 million points, I need 1 million eigenvalues. How do I find 1 million eigenvalues?
Sure. And so just to be, so for example, this system, at the end of this work, we do this complexity. This is the NeurIPS version there. Supplementals are separate. We do a complexity analysis, which shows that the Koopman method scales better then the optimize. So okay, let me put it in this way. Let's say your width and depth are both n. So the cost of optimizing per iteration is n cubed, right? Your neural network, and so we were able to show that the Koopman operator should scale better than that, depending on, well, not depending on, actually, like just clear cut demonstration. So the scaling should not be a problem. What is but you're right, like there is, again, like, there's a question of like, well, what are the limitations? Because within the theory it would seem like, well, it can do anything, right? And so the limitation is more on the side of how well the Koopman operator of the network. And also, please do realize that the Koopman operator being calculated is for the network's weight and biases, not of the differential equation or MNIST or whatever I'm solving, right?
Yes, but that's even worse, because you can have, usually the number of weights and biases is much larger, right, than the number of states of a differential equation, let's say.
Yeah, like you can have like trillions of parameters, right?
Exactly.
And so that scaling, so that's why, again, we made relative examples, because when you have a trillion parameters, you do also actually need to train a trillion parameters, every iteration, right? So those costs add up as well.
Right, but these are matrix vector multiplications when you use, let's say, stochastic gradient descent. But when you have the Koopman operator, you have to find eigenvalues. So
yes,
which is much more expensive than doing matrix vector multiplication.
So let me put it this way. Actually, again, that's a very, very reasonable point, right? I guess when you're comparing the relative costs, the trade-off is, once you have the eigenvalues, right, you can push your network all the way to the end. Would you agree with that?
It depends. It depends on what regime of training you are for the neural networks, because you know that neural networks can be in an ordered regime or in a chaotic regime, right? Depending on the variance that you have for the initial values, right? The variance of the initial conditions where you start your training. So if you are in the chaotic regime, Koopman will have trouble.
Yes, well, anything really except, classical methods usually will fail in their predictive powers. So yes, that's again, and that is one of the, what you would call, so, okay.
Let me just say, I don't want to sound, like I don't like it. I think it's a good idea. It's just, I'm trying to, like George, we're just trying to understand, because in the NeurIPS paper, you don't mention, for example, anything about specific dynamical systems, and we are in the business of solving differential equations, and we would like to see how this can be used.
I mean, again, you don't have to, as I said, we are doing science. Criticism is not only fine, it's welcome, and you're right. So first of all, yes, chaotic or edge of chaotic regime, both are going to be, even if you could potentially reliably estimate the Koopman operator, right? You are not, like, you're not going to be well off using it, because who knows what the hell where it's going to push you, right? You're right that the ordered regime is the right application, regime for this method. And again, that's sort of, that's the sort of what we are working on right now, as in, like, well, showing those things. So you are what would we call anticipating certain results, which is very, very good. In terms of the various, coming back to, like, sort of your original question, right? Like, but at least in the ordered regime, we can make a very strong claim that finding the eigenvalues of the Koopman operator, if you are aiming to train your network long enough, should more than cover the cost of construction, right? Because you can you can push your network much further ahead once you have the eigenvalues, for a very low cost in comparison with the neural network. Would you agree with that, potentially, in the ordered regime only?
Okay, I mean, I cannot, dispute that if you say that you have a proof about the complexity. So.
Okay. Well, yes, and again, that's the sort of that's more my fault than anybody else's. I'm sorry about that. But yes, you can show that given a long enough period of time that you're still intending to train, you can show that like the Koopman boosted networks will achieve their final state faster, than the whatever iterative method you're using. But you're right, there's a huge qualifier there in that you can only do this once you enter the ordered sort of, regime of optimization.
Okay, thank you.
So, okay, I was going to say a little bit about this, but now I'll sort of jump because like I don't want to push on other people's time. And so the other one, the next set of sort of, interesting ideas on this direction is this one. It's called RG perspective on the pruning of neural networks. It's not called, it's basically taking a renormalization group perspective on the pruning of neural networks and the lottery ticket hypothesis. It's available at arXiv as well, and very recent. And that's all I can say at this point about that one. Sorry about that. And thank you very much for giving me your time. Thank you very much for having us over. Are there any more questions? I think I still have 3 minutes left. So
it's all right. Do we have any more questions? Yes.
Yeah, Matthias, I see Matthias has a question.
Yeah. So thanks, Akshuna, for this very inspiring talk. I mean, you generated a lot of discussions. In the beginning, you mentioned correctly that this kind of deferred correction method assumes some smoothness of the solution. And now we have a neural network. So my question would be, do you confine yourself to smooth activation functions?
For again, in the initial proof of concept experiments, yes, but the theoretical results, no. So when it comes to sort of like what I said was the other side of the the coin, in that you can prove that the norm of the error and the norm of the loss function. For all that, we just assume that the Fréchet derivative of your equation operator exists, and the point of the domain over which you are sort of evaluating it is at that point it's invertible. Those are the only assumptions needed. But for experiments, yes, like we haven't yet used non-smooth activation functions, although accepting ReLU, I guess the classical ReLU is one major exception to that. But yeah, so usually we use for again this whole thing was first motivated by a desire to apply it to some actual scientific sort of application we were pursuing. And so our activation functions were usually sine or in some sense physics inspired, as Professor Karniadakis has inspired many people to follow. So it's usually sines or even ReLUs, we go with smooth ReLUs, etc., etc. The derivatives are just easier both to calculate, and you have the guarantee that they'll exist, right, with smooth activation. So that's why.
Thanks.
Do we have any more questions? George, you want to comment something, or we can?
No, that's good. Actually, the questions were because of our interest in this. Obviously, we're very practical people, so we want to speed up things. We want to create the next generation of pins we call chip pins. So if you can help us with this 100 times and 1,000 times faster, then we get there faster. But yes. Actually, it's really interesting to use the Koopman, the gradient flow. People are doing that, but also having this angle of the Koopman operator where you can see convergence and getting there in the landscape and so on, it's by itself, it's really interesting, irrespective of if there's actually any practical consequence of that. I don't mean to diminish the importance of the theoretical part, because that's the holy grail. If we can do that, then everything else is really not so difficult. But you're tackling on the normalization group. Are you talking about Boltzmann machines, or are you talking about actual neural networks?
Well, actually, so
I've seen before the normalization group and Boltzmann machines, but not.
This is a slightly different perspective in that. So pruning is yet another of these techniques which sort of increases the efficiency of your performance, right? And so what you essentially do is, as is well known, usually neural networks are highly over parameterized when you initialize them, right? And then there are sub networks within those neural networks that can perform as like equivalently well, right? And so pruning is this process by which you sort of pick out this. It's called the lottery ticket hypothesis, because you're essentially pulling the subnetwork is this lottery ticket you pull out of your.
Yeah, we know. Yeah, we know, but we have. Okay, but how does the renormalization group come in?
Well, so we show that actually you can interpret the IMP, which is this interactive magnetic pruning, is a way to like do this as just like a renormalization group action on the neural network. And so as soon as we show that, everything that has been done in RG theory until that point, sort of, again, proof of concept work, the applications next step, right? I just started. I just started a couple of years ago. So this is a proof of concept work.
Yeah, but we may have to bring you back for that talk. If you write one more paper then on RG, then we'll invite you back.
Yes, thank you.
Great. Thanks for taking the time today, Akshuna.
Thank you.
All right. If we do not have any more questions for our speaker, thank you, actually, for your time and your presentation. And let's move to our second speaker. Our second speaker is Adar Kahana from our group. Adar has been a postdoc here at Brown since January this year. Before joining the Crunch group, Adar worked as a senior data scientist at Microsoft and a research fellow at the Tel Aviv University, Israel, where he obtained his PhD in applied mathematics. So today, Adar is going to give an exciting talk about spiking neural networks, which are very different from like regular neural network we have been using in the past few years. Particularly, he's going to talk about the Spiking DeepONet for regression problems. So Adar, you may want to take over.
Thank you, Zongren. I hope you guys can hear me. And while you make me co-host to share the screen, I want to say that. I did. Yeah, thank you. So in the last minute, we decided to change the topic of the presentation. Let me know when you can see the screen. So today we are going to talk about the growing topic in the scientific community about how to make brownies. So as you see, there are a lot of papers discussing that. So we need to discuss that a little bit today. So first I want to present a theorem. If we, let me just simplify it. We can measure the how tasty the brownie is depending on the amount of kappa and mu, which are the sugar and butter used. The algorithm is basically to preheat the oven, put everything in a bowl, stir it, and just cook for heat in the oven for 25 to 30 minutes. I want to introduce another special thing that people do is enhancing the taste with icing. It's very helpful in my opinion. So we ran some numerical experiments, and this is the setup that we use. And I can show you that in terms of the norm that we used to verify it, it was just going very well, and we had very great results. I will be happy to share the results with everyone that wants to. Yeah, kind of upsetting in a Zoom. I hope that you guys are laughing.
The results are what? You're gonna bring brownies to all the brownie people?
Yeah, I thought that if everybody is gonna laugh, next Wednesday I will share all the results from the experiments.
Next Wednesday when we have our joint lunch. Okay, great.
Perfect.
Brownies.
Will do. Awesome. Okay, thank you. So after this breaking the ice, I will go to the main subject of this talk. So today we're going to talk about spiking neural networks. So for any of you who've seen Priya's talk in the past, like over almost a month ago in films, she was talking about spiking neural networks, something like that. I just want to assure you that I'm not going to say, talk exactly on the same things, maybe on this motivation, but I will introduce things that did not overlap with Priya's talk. So I hope that I will get pick your interest in new stuff as well. Also, I want to shout out to Jan and Leonard that are working with me on that. So yeah, I'll thank them at the end, but also thanks in the beginning. And okay, so before we start talking about spiking neural networks, I want to tell you why are we actually talking about them. So just at the end of the last discussion, a professor said about making pins 1,000x times faster, 1,000 times faster, and there are several methods to do it. And today we're going to talk about how to make them more biologically plausible. So the human brain is currently the most efficient learning machine that exists. If we like compare the human brain to artificial neural networks, there are some similarities, but for example, backprop is something that does not happen in the brain. Yeah, so we want to basically create some more biologically plausible network that works more like our brain to be more efficient like the brain. For example, here we have Lee Sedol. He was or he is basically the world champion in Go, and DeepMind actually created an algorithm that beat him, but they used 1920 CPUs and 280 GPUs. So essentially 1 megawatt of power to train, and Lee Sedol was just using his brain, estimated at 20 watts of power. Now, yeah, it's a bit hard to compare because also Lee Sedol was learning how to play this game for a long time. But I think in that paper that summarized that, they did manage to show that his brain consumed much less. And if we manage to do this as well, then even a small laptop could train DeepONets and pins like very easily. Now, I want to mention that in this talk, I'm not going to mention hardware. There are neuromorphic chips designed exactly for this kind of setup, spiking neural networks. And we are only going to talk about the algorithmic side of spiking neural networks. Okay, so continuing with the motivation, what we want to do is kind of study how the neurons in the brain function and how are they different from the artificial neural network neurons, and how we can create something that is more similar to the brain. So there have been many studies that develop components in the brain and kind of mathematically and physically structure and model them, and we can use them. And there are many state-of-the-art neuromorphic chips that know how to mimic the brain behavior. And what I'm showing here is a Wikipedia page of the biological neuron model. So it's a huge page. You're welcome to look at it. It's super interesting. But you will see there rather quickly that the human brain neuron is different from the artificial neural network neuron. And this raises questions like how do we interpret those in the brain? And also, yeah, this exactly the point of this talk, trying to create something that is more biologically plausible, more closer to the brain. So the first thing that is different in the brain, that the brain is operating on spiking data. These are basically examples for spiked brains. In artificial neural networks, ANNs, we can have like, I don't know, image data or audio data, things like that. There are signals that are not necessarily spikes. Also, in this talk, you'll see that most of the spikes will handle are binary, and they don't necessarily, in the brain, they are not exactly binary, kind of noisy spikes. But we will talk only in, we will work only with binary spikes. And so assuming that the brain, okay. And another thing I want to say about this is that those spikes are temporal. Like what we are seeing right now is spikes over time, which will be a major thing for us. Like everything that the brain handles is sequentially in the between one neuron to another neuron. There is a spike train that operates through time. And everything is getting learned in the forward propagation inside the brain, and we don't have actually backprop. Okay. So to simulate those spikes, there have been many formulations and many things. I will focus on a couple of them, and I will show you later, mostly on the integrated fire model. So I just want to introduce this. It's experiment done by Lapik back in 1907. He created an experiment on a frog's leg where he just injected voltage into the neuron until he saw a spike and some behavior happened. So since that discovery, he came up with something called the leak integrated fire, which is an ODE. I will mention it in a lot of detail later. And this, I'm showing that because I want to show you that there is mathematical formulation for these kind of components in the brain. So we can use that to actually construct some neural network that looks like the brain. Okay, so as a conclusion for the motivation, I want to show you what other people are doing in this field. One of the popular methods is doing ANN to SNN conversion, which usually means taking an already pre-trained ANN and just integrating a spiking framework into that. So just training the ANN and having it handle spikes. Usually they are highly accurate because we can preserve the architecture from the we do preserve the architecture from the original ANN, but they usually like all the other ANNs, they take a lot of time to train, and yeah, efficiency is not the matter so much. Another method to do that is surrogate models, which was I think highly visited in Priya's talk. The aim is to basically do the backprop within the SNN. So the SNN handles spikes, it has a lot of thresholding, and then we want to kind of find either a surrogate to the different derivative of the thresholding function, or saving in memory the values that were there before, and basically computing gradients in a spiking framework. And the third one, which we are going to talk today about, is pure spiking neural networks. We will talk a little bit about the impurities of our method, but I will mostly introduce how we can do it without backprop at all, without weights, without dense layers, and yeah. And at the end, I will show also things that we can do with DeepONets and actual dense layers. Okay, so now let's go into the spiking framework itself. So let's start with the data. How does the data differ from the data that we know? So in a spiking framework, obviously, we have the spiking data as well, which is binary data. Either there is a spike or there is no spike in the train. And the output from the output of a hidden layer will also be binary. So essentially all of the data that runs through our system, except for maybe the weights, will be binary. So this is very hard to handle if you think about it in terms of backprop and trying to compute gradients. Because we will use thresholding here and there to actually make them spikes. So the network itself is not differentiable. Yeah, basically this is the, and what I'm going to show now is how we take conventional data, for example, MNIST images, and convert them into spiking data. We will then talk about how do we do it for functions. Just to have a clear understanding of how we can do it, let's briefly talk about the MNIST example. What we want to do is convert a full image, like an MNIST digit image, with pixels in values from either 0 to 1 or 0 to 255, doesn't matter, and convert it to a set of images of the same size, but with temporal dependency. Okay, so we have, for example, NT images right now. And before you freak out about how much more data we are using right now and how we exploded the amount of pixels, basically, remember that the binary images can be handled as sparse data. And I will be claiming this sparsity argument a lot in this talk, because basically this is the strength of this. On one hand, we introduce a lot of new images of the binary, like all of the time-dependent images, but on the other hand, they're all sparse. So we did not contribute much to the memory consumption. Actually, we reduced the memory consumption in some sense. And how sparse, you may ask? As much as we want. Basically, this is something that we're currently talking about. We can control the amount of spikes in the encoding throughout the network. We can, for example, I'll show the method in a second, and you will see exactly how we can limit the number of spikes as much as we want. We can cap the number, have an upper bound for the number of spikes. So the most famous or the most popular method to encode images into spikes is rate encoding. What we do in rate encoding is basically take, for example, a specific pixel from the image. Let's say the example pixel here, we have some value in that pixel, let's say 0.651. We just create NTE just to make it easier. Let's say that we have 50 time steps. It will follow us through the presentation as well. So we take 50, we basically generate 50 random numbers using Poisson or Bernoulli distribution with expected value of 0.651. So in that case, we just have for each pixel a vector of size 50. And we can construct from all of them just that tensor that I was talking about. Like here now for each pixel we have 50 sized vector, and we can just construct like that. So here we can see actually 9 examples of rate encoding. You will see that they are kind of different from each other. And this is basically due to the random generation of pixels. An important thing to mention here is that this is, from this we can actually reconstruct the original image, but up to a certain accuracy. Because if we take the, for each pixel, we take the vector that we produced and just compute the, sum the number of spikes that we have and divide it by 50, we'll get something like the expected value back. So in this case, we have 50. So for pixel in row 5, column 20, we'll have like either 0.64 or 0.66, something like that, which is not exactly as 0.651. But the key point here is that this is reversible. We can, up to certain accuracy, recover the original image. Okay, another method is latency encoding, which essentially means quantization. We just use a couple of, like, depending on how many time steps we want, we just split the data into small quantiles, and every if a value drops in that quantile, then it has a spike in that time step. Now, the issue with that method is that it's a single spike per pixel. And this is why people usually don't like it, because it's like more efficient, but less data. And usually this causes like methods to fail because it's very hard to actually do the spiking training with that. So people prefer rate encoding, for example. But there are some interesting papers with the title of single spike SNNs and how to train them. Yeah. Okay. Okay. So one thing I want to do before I stop for questions is showing how. Okay, our end goal is to do function regression. So in function regression, the inputs are the x and t data, for example. Sorry, in this case, we are just interested in like y of x, that's it, or f of x. So our inputs to the network will be x's, x points, and the outputs should be y of x. One of the, we tried a lot of methods to do that. We tried the rate encoding that I just showed and latency encoding and several others. And I will later show results, but this method was very easy to understand and also gave us like very good results. Just encoding the input data, the x's, as a lower triangular matrix. So you can think about it, every time we add a delta x, we add a spike. Yeah. Okay, and I think I can start for questions right now, if there are any.
Quick question, Adar.
Yes.
Hi, this is Panos. So when you do this lower triangular matrix, so you give up sparsity somehow, right?
It's much less sparse, but we can still handle it in the sparse form. You mean like implementation wise, or just?
Oh, I don't know. I mean, you for what do you have as your, before you had these binary images, right? So in this case, what do you actually have here for this, for what you chose? So at time 0, right, that would be the first input to the network, yes, right? So that would have only just one right there in the, and then at time 0 plus delta t, you will have 1 and 1, so you will have 2 spikes. What is it?
Yes, essentially, yes.
And then 3 spikes at hitting somehow at time 0 plus 2 delta t.
Yes, yes. The thing is here,
I don't see it how it comes into the network. I mean, it's.
Yeah, it was just about what it was just about what I was about to say. So okay, in this method, for example, each sample is fed into the network as like each one of each sample is a tensor. Like this tensor is a sample. In the function regression, each sample is not a tensor rather than a matrix.
Okay.
Yeah. So this is basically the input. In that case. Yeah. And it will be.
And if you are in higher dimensions than 1, this x will be a collapsed vector of all the dimensions somehow.
That's an excellent question. I should have mentioned that the whole part of encoding, especially for functions, is still something we're working on. I will show something about 2D with x, y, and t, but you're touching a great point. What I did there is just stacking those that we see right now. So this worked, but 100% you're right, and we can do better.
Okay, thank you.
Yeah, thank you. Awesome. Okay, so I want to mention that there is not much theory around for spikes. This is a paper by Maas from 1997 proposing a theorem for noisy spiking data. To summarize, basically it states that every function can be approximated by a sufficiently deep noisy spiking network. We're trying to work on some theorems in the side, but I'm not gonna discuss it much in this presentation. So just know that there is something, but not much. Like that's what I wanted to show here. Okay. Okay. Now to the actual setup implementation, like the things that we are actually doing in this spiking neural networks. This is a very overwhelming image that I found in Wikipedia, and I really don't want you to look at the entirety of it. I just want to focus on 3 things. One of them is the membrane, which is a layer that surrounds the neuron. We will talk about it a lot. You can see it over there. The membrane decides what chemical materials to push into the cell. So yeah, you will see exactly how it controls the behavior of the neuron by doing that. These chemicals also include like charged electrical ions. So the membrane controls the input current and the voltage and things like that. And eventually, if the membrane has too much voltage, the neuron fires. Second are the dendrites. Dendrites, I'm not going to focus on them in this talk, but they're very interesting for us. They are designed to receive communications from other cells. So they, like, by moving information, we can achieve a lot. For other tasks as well. And the third one is the synapse. The synapse is essentially where the magic happens. I will get to it. So the synapse permits a neuron to pass electrical or chemical signals to another neuron. And you can immediately think about, the connection between different neurons in the brain is done by the synapse. Okay, so let's start by talking about the membrane. The membrane, as I told you in the frog leg experiment by Lapic, was found to this resistor capacitor circuit can basically simulate the membrane behavior up to a very good approximation. So in this equation, C is the capacitance, R is the resistance, I is the input current, and V is the voltage over time, which we are interested in. V rest is what the membrane voltage is at the resting position. We can also write this equation down as with tau equals RC as given here. And it's a very good surrogate model, and it's been used by many people in the field. Okay, so essentially the leaky integrated file is an ODE that we can directly solve, and we can also approximate using forward Euler to get this expression. So basically what we did in the approximation is use forward Euler and then collapse a lot of terms into beta and overload a little bit the input current. I will say right now that there are actually other models that try to formulate the membrane behavior in more accurately, like the Hodgkin-Huxley model or fractional order leaky integrated fire models, and they surface a threshold between trade-off between the accuracy of the method and the efficiency of the method. And given that our ultimate goal is to make pins much faster, we kind of rely on some approximations to make it just run much faster. One thing that we need to add to the leaky integrated fire model is the V threshold that I mentioned earlier. If the membrane voltage exceeds that threshold, it's registered as a spike in the neuron. Okay, last thing I want to add is a reset mechanism, which means after a spike, the membrane voltage resets to a certain point. So there are a couple of methods to actually reset the membrane. One of them is reset to 0 or reset to V rest. the resting position. Another is to just subtract some voltage, for example, twice the threshold voltage or something like that. And all of these reset mechanisms are used to make the membrane or make the neuron or not allow the neuron to hyperspike, avoid rapid spiking, also called overexcitement, which is funny. Yeah. Okay, so I want to show you first how the membrane voltage actually behaves with that leaf model. So in this example, we have 5 input spikes over time. And this is what happens to the membrane. We can see that after the first spike, we see the leakage of the voltage. And then there is another spike that causes an output spike. And then the membrane resets. And then immediately, kind of lucky, I don't know why, I got like immediately another spike. And then a huge leakage, and then another spike. Which
Adar, maybe use the cursor to point to.
I actually thought okay, whoops. Can you see my cursor now?
Yes.
Perfect. Okay, so this first spike is here, and then we see the leakage of from the leaking integrating file model. Then we have the second spike that was actually registered as an output spike. Then luckily we have we have the reset here. Luckily we have another spike. Then we have a huge leakage. Another spike that was also registered as an output spike. Reset, and then another spike and leakage.
So I think the point to be made here is that the temporal information is very important, because it will determine, with, like, for example, this huge leakage after the third spike, right? If the gap is big, you can see you could you could go below or above the threshold. So yes, the temporal time is, the temporal encoding is transformed into some threshold information, which is important.
Correct.
Which is different, because we don't have this temporal encoding in current neural networks.
Correct. Yeah, the temporal. Yeah, this is. If I did not emphasize this, thank you for doing that, Professor. I should have emphasized it. The most significant part of the spiking neural networks is the temporal connections between, like, everything is going through time. There are the spike trains, and everything goes through a sequential order. Yeah. So this is basically an ODE that we solve, and this is the deterministic process. And the question that now surfaces is, how do we learn? How do pure spiking neural networks do learning? And for this we have the synapse, as I said earlier. So in the synapse we have basically, the synapse is the connection between neurons, input neurons and output neurons. And we can think about the synapse as a Hebbian learning rule. The most famous one is this spike timing dependent plasticity, which I'm going to talk about right now. And that rule says, okay, let's split the neurons to presynaptic neurons and postsynaptic neurons. So since temporal, like, we have the temporal dependency, for pre and post are like neurons where they that happen in the spike train. They were located before the synapse, and postsynaptic are after the synapse. So imagine the synapse as kind of a fully connected layer, where I have Wij weights between the connection of each two neurons from the, like, between the presynaptic and postsynaptic neurons. Okay, and the rule says that if the presynaptic neuron spike before the postsynaptic neuron, then we want to increase the connection between them, also called potentiation. If the other way around happened, then it's called depression. And why is that? Why does that make sense? Because if a presynaptic neuron caused a postsynaptic neuron to spike after him based on time, then we think that there is a connection, like the first spike actually caused the second spike. If the other way happened, like the postsynaptic spike before the presynaptic, then there has been other presynaptic neuron that caused the spike in the postsynaptic neuron. So there is no connection between these two, and we want to actually decrease the connection between them. So how do we actually do it in terms of like implementation? The SDP rule in here says, okay, there are some implementation. This is a relatively easy one to both understand, implement, and use. So we have something called the SDP curve, which determines the weight change depending on the time between the spikes. If I just plot the SDP curve, it looks like that. How do we interpret the SDP curve? Let's say we have this presynaptic neuron and this postsynaptic neuron. I hope that's good. I should have, sorry. I should have enlarged the spikes a little bit. I hope you guys can see. But if we compute the delta time between the input neuron and the output neuron, we can just go to the SDP curve, ask it where are we standing, and we will get the weight change that we want to add for the connection between these two neurons. Any questions about the synapse? Great. Okay, so what other methods we have, and I'm going to show later. As you guys understand, these are just connections between neurons. Most of the people in that field, what they do is just place a dense layer between two leaf layers and back propagate and learn those connections. So this compromises, of course, the spiking behavior. It's not sparse, it's not binary anymore. We need to do backprop with SGD. Everything becomes much harder, but it's possible. And another thing that we wanted, I will show later, is just, we have the membrane, the threshold, the reset, the inhibition, the everything, like all of those, just throw it on a DeepONet as an operator and see if it manages to learn it. Yeah, and I will see soon that, I will show you soon that fortunately DeepONet managed to do that. Okay, so this image shows how the membrane and the synapse actually function together, because the beautiful image that we saw before with the decay and the leakage and the spikes and everything, it completely changes when we actually use a synapse, because you multiply the input currents with some weights from the synapse. And this is something that we get if we actually use the synapse. In this example, we can see that we had two output spikes. And yeah, I think I said everything I wanted on this one. An important thing to mention here is after we finish with the learning using the synapse, we have some output neurons that basically we need still to fit them into the data. Let's say we are trying to learn MNIST. The output of our network will have, if we design it correctly, 10 neurons. But these neurons are not necessarily matching the actual digit of MNIST, because this is an unsupervised problem. We run the data through the membranes and the synapses and everything, and we get some unsupervised results. So at the end, we can just use SVM, for example, to do that. Another issue we have with that method is that there can be a couple of neurons that learn the same thing. In this example, we can see that for the digit 5, neuron number 2 and neuron number 8 learn the same digit 5, and we do not want to have that behavior. And there are a couple of things that we can do to do that, to solve that. One of them is lateral inhibition, which basically means that a neuron will not spike like if a lot of neurons around him. Okay, sorry, I'll explain. Like a neuron will just the winning neuron, like the neuron with the highest voltage, will spike, and the surrounding neurons will not spike. So this is how we can handle inhibition. Another
is that the winner takes all?
Yeah, exactly. So in this case, we can, the winner takes all can be implemented in a couple of methods. And this is one of the things that I've seen that people do to get the winner takes all. And two more things that or three that I want to address before we see the results. I talked about overexcitement. So overexcitement in the brain, and obviously here, is not a good thing, because we have the trade-off between how many spikes we have, and that will, like, more spikes will give us more accuracy, less spikes will give us more efficiency. So if a neuron just overspikes, that's bad for our efficiency. So we want to be able to prevent a neuron from overspiking. How do we do that? We have a couple of methods. One of them is dynamic thresholding. We can just higher the threshold of the membrane every time the neuron spikes, and lower it maybe if it's very idle. Also, we have something called refraction, when we kind of make the neuron go to sleep after a spike. And the last one is homeostasis, where we scale the synapse weights down and up depending on the spiking activity. Okay, so about the numerical experiments that we conducted. So the first one is we kind of called it the naive network. Apparently everybody does kind of this stuff. No, sorry about it. I need to take it back. First experiment I want to show you is a pure SNN, zero backpropagation, only like synapses with the STDP rule that I mentioned earlier, leaf neurons, just pure SNN. So in this case, we have the input MNIST. We are working with the MNIST data set. So the input will be 50 by 784. And then we have one layer of 50 by, let me take the data for it. So 50 by 784, it's the input encoded MNIST data, spike encoded. Then we have a layer of 50 by 100, and then a layer of 50 by 10. And yeah, so this is the, like, in the initial stage where everything is still initialized, this random initialization of the weights in the synapse. And this is just kind of examples, like these are 50, this is a sample from MNIST, and this is how it looks like. And this is some spikes that just, random spikes that were produced by this random synapse.
Excuse me, quick question.
Yes. Yes.
In the input spikes, what are the different colors? I don't understand there.
Yeah, so imagine the images that I showed before. Okay, wait, let me just get that, it would be easy. Oh, there. Take one of these images and stack it to a vector.
Okay.
Now you have 50 of those because they are time dependent, and we have NT equals 50. So we just stack them as a matrix of size 50 times 784, which are just the spike encoded MNIST data set. This goes through a synapse, which these are the weights of. And this is the input currents that go into the membrane. Then we have the membrane, and we use the STDP rule to update the synapse. And the membrane creates the output spikes. After the synapse, we have the output neurons and output spikes, and we can see them here.
Okay.
And same we have in the...
So the vertical axis is like the time that you use this NT, right?
Correct. Yes.
And then you said the horizontal axis are the different samples. Or what is that 784?
784 is, okay, so now we have a single sample, a single MNIST image. 784 is if you take the binary encoded image and just make it a vector. It was 28 by 28. So,
oh, I see.
Yeah. So it becomes a vector, and then you have 50 of them because we created one for each time step. Yeah.
Okay.
But it's a great question because here, like, we can look at them as 784 input neurons that results in 100 output neurons, which go to another layer of leaf plus synapse. And at the end, we have just 10 neurons for the prediction.
Okay. Okay.
Yeah.
That actually helps a lot to visualize it like that.
Yeah, I should have. Yeah.
Okay. So the horizontal axis is the length of the vector that goes in, and
Exactly.
then the vertical axis is as they come in time, right?
Correct. Exactly.
Okay. Thank you.
I should have put the axis labels. I will do that. Thank you. Okay. Now, after one sample, like in the second MNIST digit that we feed to the network, we can already see some activity. We can already see that the synapse is picking up something. Here we not yet. In the third one, we can already see that the first layer is already like learning pretty well and producing one major spiking neuron. By the way, here I did not do to create these plots. I did not use inhibition nor homeostasis, refraction, and the dynamic thresholding. So here I'm allowing overspiking just to, like, to make the point and show you how it behaves. So here you can see overspiking. This is what we mean by overspiking, like spike, no spike, spike, reset, spike, reset, spike, reset. Yeah. After after 30 samples, we can see like very distinct learning by the synapses. And after like 50 samples, we can already see that it kind of converged. And think about it, like 50 MNIST samples to kind of reach the maximum. So I'm not saying these results are good yet. Okay, I'm saying that there is a lot of potential. Like after 50 samples, and I've seen it in a lot of papers, like people use like a very low number of samples to achieve very high accuracy, actually. Now, why am I not saying that these are good examples? Because as you see, like we have only one major like pixel here that operates in the second synapse. So this means that we will always have like the same spike in the same neuron. This is not so good, and I'm purposely giving this example. I did get it to work a little bit better with different parameters and things like that, but mathematically there is because we do not cap the changes in the STDP-Hebbian rule, we do not cap the change, so it creates a long tail distribution, which can be at some point look like that and basically converge to something that we don't want, something fixed. There are many ways to overcome this as well. I have like 3 or 4 papers that I need to implement in order to solve that. But I just wanted to show you that, like, statistically, like, we will get these results a lot with this specific STDP rule because it's considered highly unstable. And unless we carefully choose a pre and a post, it will probably get to this point. This is what I said before about we just need at the end, like, take something like these spikes and connect them to the actual digit, which we can do with SVM or some other like costless method of something that we can use. But we can also use a dense layer with softmax to just do the learning at the end. Now, this will not cost much because we are just creating a 10 to 10 dense layer, and we backpropagate only on the last hidden layer. So this will be very cheap. And yeah, this should be actually good. Okay, so we talked about sparsity, we talked about parallelism. So this is something I did not say. So parallelism, basically those in this specific paradigm in the HTTP, we can, because we take a sum of the weight changes, we can batch the data and send the batches into different compute units and eventually sum all of them back. So there are some papers that suggest to do that. I have not tried that because it does take in account some initial state of the synapse that needs to be shared between all of them. And I think it's not that easy plug and play batch and put in different nodes, but it's definitely possible and doable, and people do that. And if we already talk about sparsity, we did manage to play with the sparsity, and we got like 100 times less data usage when we use the sparse TensorFlow code. Okay, so what about function regression? For function regression, we have two methodologies that I will show right now. One of them is just taking the leaf neuron, pushing it to a static synapse. In this case, I mean, I'm not using the STDP rule, the unstable rule. I'm just using, like, imagine an identity function that takes spikes, pushes them into the membrane, and produces the output spikes. So there is no learning at the synapse at all. The only learning that's done is using the fully connected layer at the end, which is used to produce the function data. So again, the inputs are, we take the points in the x-axis. We use, for example, the triangular, I think here I use the rate encoding actually. I use rate encoding to encode the data and create the 1 times nt times nx data, pushed it into the leaf layer, produce the output spikes, and let the fully connected layer decompose them into function values. Basically, we backpropagate to learn y of x. Yes, and these are some results that we got. This is, for example, a square function and a noisy square function. And we can basically conclude from here that the function is able, the SNN is able to do the functional regression using the dense layer at the end. And as I mentioned earlier, we did also try with a 2D function. This is a Ricker wavelet given by this formula. And we got like very good L2 error. Basically, it kind of, so I did not normalize the error based on like, you can divide it by the size of the grid, which is 10,000. So this is pretty good. Yeah, and to do that, as I mentioned earlier, what we did is just take the data of the function, stack it as one long vector, use tile to get the spike encoding of the x-axis, and then just reshape it back. Sorry, let the network infer, and then reshape it back to this. Okay, and another thing is, as I also mentioned, is just, you know, take the leaf function with the reset and the membrane with the reset and the threshold and everything. We try to throw everything at it to get like spiking data after a couple of iterations through the leaf layers, and just see if the DeepONet framework can actually handle it. So the input to the branch were Gaussian random field functions, and the input to the trunk was basically the data, the spiking data after a couple of leaf iterations. And yeah, and then we just multiply the results to get the output, which is the actual function data. And I want to show this image, which shows that, yeah, the DeepONet was able to actually solve it as well. This was done with the lower triangular. With the other ones, we got much less accurate results. And here, the interesting discussion is these step functions are based on the time dependency. Like if we, for this, I think we used either 32 or 50 time steps, which is a very small number. If we could use, let's say if we used like, I don't know, 200 or 1,000 time steps, it will be much smoother and much closer to the actual solution, giving us a much lower error. And by the way, if I compare these results to these results with the same function, the DeepONet actually managed to be more accurate. These results are more accurate. Okay, so a couple of things that we want to do in the future is trying to figure out how to make the pure SNN training with the synapse and everything, comparing to benchmarks to, for example, MNIST benchmarks, if we can beat it with the spiking. And there are also benchmarks for like spiking frameworks. We want to try to beat them. One thing that we are working on right now is trying to replace the leaf layer with a trained DeepONet. So essentially just create a DeepONet that does the membrane. That's it. Not the entire architecture, just a membrane done by DeepONet, plug it into the SNN. What we achieve from that is A, we will be much faster because DeepONet can do it basically for free. And B, we do not need to iterate over time. We'll just get the output spikes immediately, yeah, which is also A, being much faster. Yeah, and maybe in the very, very far future, try to test it on a neuromorphic simulator or computer. And as I said, thank you to Chan and Leonard for working on that with me. And I think right on time. If there are any questions, please.
Hi, can I ask a quick question?
Of course, yeah.
So from what I saw, the way that you implemented it, it's like, at least when you also use the DeepONet, that you use it's like you learn features there, right? That if you look at the trunk, what goes in, and then after the spikes output, it's like you have learned the feature, right? Mm-hmm. Which then you feed into the trainable part, right? Which is the two fully connected layers.
Yes.
So in this case, what goes into the branch for the regression example?
Yes. So in this example, we use the Gaussian random field functions. Yeah.
Okay, but are you trying to reproduce Gaussian random fields?
So yeah, that's a good, I think you're touching a good point. We kind of didn't even know what we are trying to reproduce because the output spikes are, I don't know if to call it a stochastic. This is something that we have literally no idea how it behaves. Like there is no governing equations. Everything is thresholded, so you don't have any like differentiability. We just said maybe there is an operator there, maybe, and let's see if the DeepONet can actually learn this operator.
Okay, but this operator maps the GRF to what?
Let me think about it.
And in the trunknet, what would you put in the trunknet for this example?
As an input or as an output?
Yes, as an input. What goes into the trunknet? I mean, these spike trains, what do they represent?
So these spike trains are something like this.
Okay, but in your example, with the GRF, do you also take the sample from the GRF and you translate it into something that goes into the trunknet?
Not that I recall. Jian, maybe you can jump in, and is Jian here maybe?
I mean, what I'm trying to understand is what is the input and what is the output here? You're trying to learn functions, right? To do regression.
Yes. So, yeah, to the branch, just input just random functions and the and coordinates on these functions, and to the trunk we feed the spike encoded data. And
when you say spike encoded data, what are these data?
These
are from MNIST, right?
Yeah, okay. So you can also think about if we do functional regression. So it's wait, sorry. It's very this.
These are the x's, but you're trying to learn y of x, right?
Yeah, the y of x, yeah, it's given by the function values. Like the function values are known and are used for the training with the DeepONet. So the function, like imagine that you have x in a very weird shape and form, which is the lower triangular that went through the leaf and the static synapse and
okay. So
spikes.
x is like the independent variable that somehow you translate into a spike train and you feed it through the trunk. Okay, I understand.
Exactly. And the y is exactly the corresponding function values to those x's that are on that weird space.
Right, but your function y of x that you're trying to learn is a very specific function, right? I mean, if you evaluate, when you try to evaluate this construction here, you will have to put something in the branch, right? A GRF sample.
Mm-hmm.
So when you feed in a GRF sample, you will get some non-spiking output, right? But if I feed another GRF sample, will I try to learn another function?
When you feed, so
that's what confuses me.
I think essentially yes. If you feed, yeah, definitely. If you feed different functions, you will get like these are all. We did not retrain for each one of these graphs, basically.
I know, but yeah. What did you feed? I mean, you fed a random GRF that somehow tries to get translated to a function y of x.
I feed a random GRF.
Adar, I think you forgot to say what is the task.
Yes.
In the previous one, before the DeepONet, go back one. Yes, here. What about functions here? It was clear, I think, what was going on.
Mm-hmm.
But now are you trying? I think that before you went to DeepONet, you were trying to learn a single function.
Correct.
But now with DeepONet, you're trying to learn a whole class of functions, right? That's why you have 4 results that you show later.
Yes.
So is this like the GAN approach where you feed something random and you try to get a function out of it and some output to generate an output? That's what I don't see the connection between. I give you a function, right?
Mm-hmm.
Which is y of x is equal, I don't know, x squared plus 1, okay?
Mm-hmm.
How are you going to try to represent it with this construction that you have here? What are you going to feed into the branch net? I think I understand what goes into the trunk net, but I don't see how you're going. I don't see any features of the particular function x squared plus 1 that are fed into the problem so that I can expect the non-spiking output to be a function which resembles x squared plus 1. That's what confuses me. I mean,
maybe Jian, can you unmute yourself and answer? Or he's eating his lunch, maybe. Adar, I think he's
Yeah.
not available, so you have to answer the question.
Yeah. So, let me think about it, because I'm not sure I'm 100% understanding how to.
Go to the results.
Go to the results.
Yeah.
For example, you have what you say the truth is the blue line here, right?
Yes.
Which looks like a parabola. So,
Right.
and you try with your DeepONet, spiking DeepONet, right? To get a spiking output, which when you evaluate at different x's, it will give you something that looks like the blue line, right? I think that's what you're trying to do. That's regression.
So just to clarify, when you mean spiking output?
Non-spiking output. I mean,
Okay.
the output of the spiking DeepONet.
Yes.
You want it to be able to be a function of x, right? And then you plug in the trunknet some value of x, and you
Yes.
plug something into the branchnet, which I don't know what it is, and it will give you an output which be some point close to the corresponding point in the blue line, right?
Yeah. So if I remember correctly, the input to the branch are completely random functions that behave like this parabola, and then what we do is we assume that to the trunk, exactly as I said, we have some x that looks very weird, but the y is on the correct space, like it's function values that are not spiking, and they are correctly learned, and
so somehow I don't understand how a particular function, let's say the one on the left, right, the blue one, this parabola on the left, I don't know how this construction that you have will be able to distinguish between one function, which is the function on the left, versus the function which is next to it. I don't see what goes into the branchnet that somehow will force this construction that you have to produce an output that distinguishes between these two different functions. That's the problem that I have here. I don't see it.
Okay.
There has to be some information that goes into the branchnet that distinguishes between the four different examples here. Otherwise, how do you know what will the output be? It could be anything.
Yeah, let me double check that, and I will write you back, because I'm not completely sure.
Unless what you feed into the branchnet is something that is a GRF, which is close to these blue lines to begin with.
So yeah, I think that's, yeah, but this is what I said earlier. Like we use the GRF is in some sense similar to those blue lines. Yes.
But if it's similar, are you trying to learn the identity?
It's not the identity. It's yeah. Let me just get you back on that, because I want to check.
What is the GRF?
Obviously, it's learning something. I'm just trying to understand what it's learning.
Yeah, GRF of what?
Yes.
Yeah, that's the other thing. Was GRF of what? At what wavelength? And then what is the loss function there that would allow you to get this, not another bunch of random functions?
Right. So yeah, right. I'll have to look again at the code and tell you that, because I don't remember right now GRF of what.
Okay. Yeah. All right. Thank you.
Yeah, sure.
I think we rely on Chian to be here, but he's not. But he did the examples, he did the experiments, but.
Do we have any more questions? Matthias, you want to ask something? I saw you show your, turn on your camera. Yes? You want to ask a question?
Yes, yes, thanks. Maybe a short question. So you modeled these synapses using RC network.
The membrane as an RC, yeah.
Yeah, okay. And then, I mean, the most important parameter was this threshold for the potential. So, I mean, there's a value where when the neurons starts to spike. So how did you determine this V threshold? Is it just a tuning parameter, or how did you get this value?
That's a great question, and which I myself asked when Priya gave her talk. So and may I like elaborate it a little bit? So there are a lot of parameters here. The threshold, the reset mechanism, we can look at even the beta here. There are the R and the C of the RC circuit that we can choose. There are the inhibition parameters. Like there are tons of parameters that. So there are rules of thumb to choose them, but sort of to mimic what happens in the brain. For example, the time step should be 0.2 milliseconds because this is the time it takes a pulse to go from one neuron to another. So to choose threshold equals 1 in this case, or a little bit above 1, it was just because the spikes are of magnitude 1, okay? So it's a common threshold to take if you're using, like if your input data is 1, then the threshold can also be 1. But there has to be done some work on what are those parameters, and not only the threshold, a lot of them, what are they in the brain to actually understand what we want to put in the code. Okay, so far we just did something that makes sense in terms of like all the parameters that we use in this program, and that's it. So I don't have a scientific answer for that. Just yeah.
I mean, it's clear that this value must be larger than the value of one single spike. But as I understand it, it must be supplied by the user.
Yes, definitely. So in most of the packages that do this kind of so we wrote our own code to do that, and there are many other codes that exist there, and we got some inspiration from them. So almost all of them use like 1 or a little bit over the threshold. There's one specific one called Brian too. I think that they do like more. They offered some more closer to reality parameters. But like everything should like synchronize. Like if you just change one of them, it might do bad for the system.
Yeah. Thanks.
Yeah, definitely. I'm not an expert on how those actual components in the brain, like what is the threshold in the brain, what is the time delta time in the brain, everything like that. I'm not an expert. Like I read a lot, and the go-to was to just take something, make it work, and then if we really want to dig deep and see how it's done in the brain, then there has to be some research done on that.
Leonard, do you have anything to add? I don't know if I saw him.
Yeah, I'm here. I don't really have anything to add to the presentation at the moment.
Okay. Can you tell us like the MNIST? Did you run the MNIST example or?
So those are being ran currently. So the experiments that I'm currently doing is just a proof of concept with to see if the Spiking DeepONet with the spikes passed in can beat other SNN benchmarks for the MNIST data set.
So to answer Pano's question, what do you put as the input to the DeepONet, to the branch of DeepONet?
In the MNIST example?
Yeah.
In the MNIST example, the input to the branch are spike encoded digits.
Let me clarify. In the MNIST example, it's completely different. It's quite the opposite. Like the spikes go to the branch and not to the trunk.
I see.
And
So it remains to be seen what the with the function, what goes into the trunk and what it's, because only X goes into the trunk for all this. That's a lot of infrastructure to put in one independent coordinate.
I agree with that. We're just exploring, what we can do and how what accuracy we can obtain with these different formulations.
Okay.
And I'll definitely get back to you on that, and I'll happily continue the discussion and figure this out. So we'll get an answer for that.
All right. If there's no more question for Adar, thank you, Adar. Did I hear any question, comments from the audience? No. Okay, so this is it for this week's Crunch Seminar. Thank you, guys, for joining, and see you next week. Bye.
Bye.
Thank you.
Bye. Thank you.